In this video I'll be going through task 5, the final task of further mechanics and electromagnetic fields of Edexcel Unit 4. Okay, so let's get straight to what it's about, which is mainly magnetic fields and how they link to the left-hand rule, and electromagnetic induction and the right-hand rule. Okay, so we're talking about generating electricity and using electricity to apply a force on either a charged particle or a current carrying wire. We should make sure we get them right way around. So explain how magnetic field can be induced around a wire, not really in a wire. It's current induced in a wire, magnetic field around a wire. So magnetic field can be induced around a wire, and wire current carrying wire experiences a force and magnetic field. So let's do that bit first. Okay, so if we've got a current carrying wire, we use the right hand screw rule to figure out the direction of the magnetic field that's acting around us. So it's like right hand screw rule. So whichever way the current's going, that tells us essentially the orientation of this magnetic field that's around it. Okay, where are we? So any current carrying wire will have a magnetic field around it. Okay, so explain why current carrying wire experiences a force and magnetic field, because of the fact the current carrying wire has a magnetic field. So remember, if you have a magnetic field around this current carrying wire and you put it on top of a balance and you zero it before any current flow goes through there, if you then turn it on, this might pull up, therefore decreasing the mass, or might push down, increasing the mass, depending on the direction of the current. Okay, include equations of flux and size of magnetic force experienced by the wire. So the main one is this one over here. F equals BIL sine theta. That's going to tell you the size of the force that's actually felt. Remember, you got the idea of phi is equal to n BA, okay, as well. Include a description of Fleming's right-hand rule. Okay, so left-hand rule. So remember, these are all about the idea that they've got to be at right angles to each other. Okay, if everything's at right angles to everything else, you get the maximum force. That's why there's the idea of sine theta in here, because sine 90 is 1. If things are not at right angles to each other, then you're not going to get the maximum force out of the situation. Okay, you're going to get a sine component of that, essentially. So left-hand rule essentially is where you use your thumb, your first finger and your second finger to figure out the direction of either the magnetic field, the force, or first finger field, second finger current, magnetic field, first finger field, second finger current, and thumb for force or thumb for motion. Okay, so magnetic field, the current, or the motion. You can figure out. We'll zoom out slightly so you can see my whole hand. Oops, that's zooming in. There we go. Okay, so that's the sort of thing you try to set up with your hand. Okay, I'm hoping my camera doesn't invert this. Well, it can't because of the handwriting, but I know occasionally it's done that in the past. But there you go. That's the way in which you try to set up. So first finger, you always point in direction of the magnetic field from north to south. Second finger of the current, that's conventional current, remember. And the thumb tells you the direction of motion. Okay, the direction of the force is being applied in. Next, I know there's another video, another explaining everything task underneath. To describe the process of electromagnetic induction, include an explanation of Faraday's law, Lenz's law, and Fleming's right-hand rule. Okay, so electromagnetic induction. So essentially, you've got to have a conductor cutting magnetic field lines. That means that a potential difference is set up. If there's a complete circuit, a current will be set up, and therefore you've got electricity essentially. So you've got to have a changing magnetic field. So either if this is my magnetic field line here, so say it just keeps on going from the end of my finger. Imagine it kept on going from the end of my finger, and here's my actually, let me draw it out so you can see it. Here's a magnetic field line that's going from north to south. Okay, here's my current carrying wire, so the pen's going to act as my current carrying wire. If it's stationary in there, there's no changing magnetic field. If I moved this magnet, so in other words moving the piece of paper, okay, the magnetic field is changing inside this piece of wire, therefore I am going to get some current induced in there. Okay, so whichever way I move it, there's going to be a small current induced in there. Again, dependent on a sine factor, which is involved in this as well. But if I moved my current carrying wire, that would also induce. If I moved my wire, that would also induce a voltage in there, because the fact the magnetic field is changing. There is a change in magnetic field relative to the motion of my conductor. Okay, so that's essentially what's happening there. Faraday's law, you can pick straight off the equation. Lenz's law is a minus factor of that, and the right-hand rule, okay, is for generating electricity. So first finger field, second finger current again, but the thumb this time is for motion, the motion in which direction the conductor is moving. Okay, motion in which direction the conductor is moving. So let's go get Faraday's law and Lenz's law off this sheet. Right, so there we go, Faraday and Lenz's law. So Faraday's law is the EMF is equal to the rate of change of flux. Okay, so the number of coils times by flux over time. Okay, so it's changing, that's what the D's are. The minus factor is Lenz's law. So remember, Lenz's law tells us that the induced EMF acts in the opposite direction to the EMF that caused it to come about. Okay, so this essentially means that there is a magnetic field acting against the magnetic field that produced the secondary magnetic field. Okay, very, very strange idea. It's how lifts work. Well, it's one of the safety features in lifts. And it's also one of the safety features in roller coasters. So the magnetic field that's produced by the induced voltage opposes the magnetic field that created the induced voltage. There we go. Hopefully you've got it from that. Play that sentence back a few times if you need to. So, first question. What is meant by a uniform magnetic field? Okay, so if we've got a uniform magnetic field, that is the idea that the magnetic flux density is constant or the magnetic field lines are parallel. So when we draw the field lines in there, they will be parallel, or if we draw the field lines in there, they'll be parallel. But the idea is that flux density throughout that is constant. Determine the size and direction of the electromagnetic force that act on L and M and N and O on the square of the wire. Okay, so we've got to use the information that we've been given, essentially, which is current. We've been given the length, so remember we've got to convert that into meters, so that's 1.5 times 10 to the minus 2, and we've given the strength of the magnetic field. Okay, so there are three things that we need. Okay, so that's F is equal to BIL. Okay, so remember this is a square, so each of these is 1.5 in length. So the idea is the force is going to be 2.4 times 10 to the minus 4. So that's 2.4 millinewtons. Okay, and you figure that out by doing the straightforward calculation of timesing that by that by that. Okay, nothing else to it. Those three numbers times to each other, but by remembering this times 10 to the minus 2, and by remembering this times 10 to the minus 3, because it's microteslas. Okay, so remember the force on LM, okay, is going to be downwards into the paper by using the left-hand rule, and therefore the other one must be out of the paper. There is no force, this is the next question now, there's no force in terms of M and N and O and L because of the fact that they are parallel to the field lines, therefore there is no change in magnetic field. Okay, the other ones are perpendicular, so they cut the magnetic field lines. The effect on the square, I think is the next question, if I remember correctly. I've done this question a few times. Yeah. What effect will the forces have on L and M and N and O on the square of the wire? Okay, so it will cause it to rotate because of the fact, and therefore cause it to spin, because one side is having the force down, the other side is having the force up. The magnetic poles are now moved further apart. Describe and explain what effect it will have on the magnitude of the forces produced on L and M and N and O, assuming the current of 2 amps is unchanged. It reduces the size of the forces because the flux density is now reduced. Okay, things are more spread out essentially. The magnetic field is more spread out, so the magnetic field strength is reduced. Okay, or B has been reduced, or B field has been reduced. You can say it in those ways if you wanted to. Okay, nice opening question for 8 marks there. Question 3. Okay, so we've got the idea of a positive and negative plate. You've got positive ions entering this as magnetic field that's acting into the page here as well. Okay, so we've got electric and magnetic field in this situation here, and they've defined all the letters they want you to use up here as well. So pause the video if you need to catch up. The electric field causes a force on an ion between the plates. State the formula for the magnitude of force. Magnitude of force. So we've done it before. We've done it in a previous video. F is equal to E times by Q. Okay. In which direction does this force act? Okay. The electric field causes a force on an ion when it is between the plates. It's a positive ion. It's going to go down towards a negative side. It's going to go down the page. Okay. The magnetic field causes a force on the ion which opposes the direction of the force from the electric field. So the magnetic field is going to apply force in the other direction. But a suitable combination of values of V, E and B. All right, now we know F is equal to Bill, but we also know from substituting into this, F is also equal to BQV or BEV in terms of BeV, if it's an electron as a charge. Well, it's not an electron, it's a positive charge, so let's use the BQV. Okay, so we know that. We'll probably need to use that. You can see that they've mentioned B and V. That E is the electric field strength, not the charge of an electron. Okay, and the motor forces balance each ion. Okay, so the electric and magnetic forces balance each other. So that's the magnetic force. We know it's a magnetic force because it's got capital B in there. The electric force we just said was E times by Q. So those two balance each other. So it will go in a straight line through there. Calculate the value of V of the ion to travel straight through. And they've given you E, they've given you B there. All the other information's above. That V is too big. Should be a small v. Sorry. Over here as well. There should be a small v. Because it's velocity. So let me write that again so it's nice and neat. So B QV is equal to EQ. Okay, so the charge of the particle disappears. Okay, it's not required in terms of this calculation. So all you actually end up with is velocity is equal to E over B. Okay, and you've got those two numbers there. That allows you to figure out the velocity. Explain why ignoring the effect of gravity on the ion is justified. Okay. Well, remember the weight of this is going to be a lot less than the force of the force that the electric field applies on this object. So I've just written the equation down for the force that the electric field applies on this object. Let me just zoom the webcam in slightly. There we go. So the F equals EQ is going to be much greater than mg. The mass is so small. Okay. It's not even worth considering. Saying the mass is so small would only get you 1 mark. Okay, saying gravity is a weak force would only get you 1 mark. Okay, or saying the ion moves very fast would only get you 1 mark. It's the idea that this mg is so much smaller than the charge due to the force due to EQ. Well, if it's so much smaller than that, then therefore it's also going to be so much smaller than that. So it's not even worth considering. So it's proving the negligibility, if that's a word, of the weight. Okay. Question 14. If I remember the last question, let's just double check that. I think it's quite a long one, but I remember it being the last one. Yeah, it is. No, it's not too long. Right, okay, so current carrying conductor is situated in a magnetic field. Describe how, it's not a good start to the question, I think I've deleted something from there by accident. Describe how you could demonstrate that the magnitude of the force of the conductor is directly proportional to the magnitude of the current in it. You may wish to include a diagram in your answer. You may be awarded for the clarity of your answer. Well, the question isn't very clear, but I'm sure you'll come up with a clear answer. It's clear what they're asking about. They're asking about how can you prove that F is proportional to I. Okay, so the easiest way to do that is by saying that F is going to be your mg, and then going back to this setup that we had over here. Okay, and then plotting a graph of varying currents against the change in force that actually applies. Change in force picked up from the change in weight, which essentially is picked up from the change in mass of this. Plotting a graph of that, so you end up with a graph of force against current. Remember, current across the bottom because that's what we're changing, and force on the side over here. And that should be a straight line. Okay, if we did that, that should be a straight line. So the force is coming from this, the change in mass that occurs there, times by gravity that allows you to figure out the size of that force. And the current is just picked up from an ammeter that's connected to that wire. Pretty straightforward. Okay, so you've got to make sure, this is reading from the mark scheme now, that there's a method of producing a varying direct current. Okay, so that's going to be that connected through the power pack. The wire is perpendicular to the magnetic field, so I've shown that there. This wire's coming out of the page. Magnetic field could be going from left to right or right to left. A method of measuring the detained forces. So essentially we've got the idea of the scales in there that allow us to measure the size of the force. And the fourth mark comes from, again, drawing that plot to prove that it's directly proportional. So we've got a situation here where we've got some copper tubes, an aluminium rod across them. magnetic field. Okay, it's going into the page. That's what the X's mean. It's going into the page. You've got an area of here of 30 centimeters cubed. Okay, the magnetic flux density of the field is 0.2. Calculate the initial acceleration of the rod, assuming that it slides without rolling. So in other words, there's no rolling friction when the current in the rod is 4.5 amps. So we know the current. We want to figure out the size of the force. We've got A for the area. Okay, so that's going to be useful potentially. We've got well, it might not be the area they actually want. They might want the lengths. Okay, so we're going to think our way through this carefully. So we want to figure out the acceleration that's taking place. So we know that acceleration is linked to F and M. F equals ma. Okay, let me zoom this out again now. So from F equals ma, we also know that F equals bil, as we've got up here. So we've got our B, 0.2. Have we got our I? Yes, we have, of 4.5. Have we got our L? Well, it's going to be rolling in this direction. Okay. No, so it's the length of the tube that we want. So it's 5. So but it's 5 times 10 to the minus 2. So you need to multiply those three things, and you end up with 4.5 times 10 to the minus 2. Okay. And then we want acceleration. So acceleration is to be force over mass. So you take that force of 4.5 times 10 to the minus 2 and divide it by the mass of this rod. Well, the mass of the rod is 50 times 10 to the minus 3, because that's in grams. So you should end up with about 0.09 meters per second. Let me guide you through that carefully then. So F equals BIL to begin with. So our B is going to be 0.2. Our current is going to be 4.5. And our length is going to be 5 centimeters. That's 5 times 10 to the minus 2 centimeters. Okay, so that ends up with 4.5. Yeah, 4.5 times 10 to the minus 2 is what you end up with from that. Okay, so that is the size of our force. That then goes into the idea of F equals ma. That's our F. Okay, our M is 50 times 10 to the minus 3, because it's in grams and we want it in kilograms. You divide those two together and you end up with 0.9 meters per second squared. And that's the initial acceleration. Okay, so it's quite shifty that they put the 6 and the 5 in there, and all you actually need is the 5. Okay, that's the 8 marks for that question, and that is the end of the ISP on further mechanics and electric fields. Okay, so remember there's another part to Unit 4, and that's particle physics, which forms the majority of Unit 4. So make sure you go through that ISP and watch the videos on that as well. Thank you very much for listening, guys, and if you've already done the particle physics video, then you've done it in the wrong order. This comes first, really, because you need to know about circular motion, you need to know about electric fields before you do particle physics. But if you have done it, then good luck in your exam. Thank you very much.